Let's look at problem number 5 on the example problems. We're going to use this diagram to answer the questions below. We have 3 separate charges, 2 negative charges and a positive charge. Question A says determine the magnitude and direction of the net electrostatic force on charge number 1. So that's this charge right here. Now, the problem is we have 2 different charges that are interacting here. Charge number 1 and 2, they're both negative, which means that's a repulsive force that's caused by the interaction of 1 and 2, which I'm just going to abbreviate that way. There's also a force interacting between charge number 1 and charge number 3, which is an attractive force, which I'll call F1-3. That's the attractive force that's trying to pull it over to that positive. So what's going to be more important, the negative repulsive charge close together, or the negative and positive attractive force that's far apart, but there's a larger magnitude of charge here? So let's find out. So the force that's acting between 1 and 2 is equal to K times Q1 times Q2 divided by the distance between them squared. So we have 9 times 10 to the 9th Newton meters squared per Coulomb squared times negative 4 coulombs times negative 1 coulomb divided by this distance, 2 meters, quantity squared. Negative 4 times 1 is of course 4, and 2 meters squared is of course 4, and that's multiplied by our 9 times 10 to the 9th, which I didn't write, which would go in here. So we end up with the force being 9 times 10 to the 9th newtons. That's the force that's repelling these two from each other. So what about the attractive force between 1 and 3? I'll denote that with a 1-3. That's equal to K times Q1 times Q3 divided by the distance squared. So that's equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared times our negative 4 coulombs times our value over here, 6 coulombs, divided by the total distance. So the total distance from 1 to 3 is 2 meters plus 3.5 meters. So that's 5.5 meters quantity squared. We can see the 9 times 10 to the 9th is being multiplied by a number that is equal to 24 coulombs squared over 30.25 meters squared. This is 5.5 meters squared. This number is less than 1. Up here the number is greater than 1. So this force is going to be greater than this force. But let's see what this force is. 9 times 10 to the 9th times 24 divided by 30.25, and we get 7.1 times 10 to the 9th newtons. And this is negative because we have a negative sign here. We have a negative here, so this force here is negative. The negative sign doesn't indicate the direction, it only indicates that this is attractive. So this is repulsive and this is attractive. Which one is going to win? The repulsive, 9 times 10 to the 9th. The attractive, 7 times 10 to the 9th. The repulsive force is going to win, which means this is going to be pushed to the right. So we can subtract these two. 9 times 10 to the 9th minus 7.1 times 10 to the 9th. And the net force, F net, is going to be equal to 1.9 times 10 to the 9 for a magnitude. And which direction is that going to be? It's repulsive, so it's going to be going that way. So we'll say that's to the left. Units there are newtons. So the next question says, determine the magnitude and direction of the electrostatic force on charge 2. Well, we've already determined the force between charges 1 and 2, so we can reuse this number right here. It's equal to 9 times 10 to the 9 newtons. Now that force on charge 2, though, is in which direction? 1 and 2 repel each other, so the force on charge 2 is acting to the right. We need to solve for the force between 2 and 3. So the force between 2 and 3 is K Q2 Q3 over D squared, which is equal to 9 times 10 to the 9th. The units newtons meters squared per coulomb squared. And this is times the -1 coulomb times the 6 coulombs divided by the distance between them, 3.5 meters. That's squared. And when we solve this, we end up with a -4.4 times 10 to the 9th. I know you can't see that. Let me rewrite that. 4.4 times 10 to the 9th newtons. What is the direction of the force on 2 between 2 and 3? So this is an attractive force. So there's a repulsive force between 1 and 2, which is pushing it in this direction. And then there's also an attractive force, which is pulling it in this direction. So the two of these are going to combine together. The magnitudes will combine. So we have the net force is equal to 9 times 10 to the 9th newtons to the right plus 4.4 times 10 to the 9th newtons to the right. So we end up with 13.4 times 10 to the 9th newtons. We rewrite that in proper scientific notation. We have 1.34 times 10 to the 10 newtons to the right. So that's our answer for part B. The last part, part C, I'm going to take this and move it up if I can. And let's look at C. We already have found the force between 1 and 3 in A. And that force between 1 and 3 was 7.1 times 10 to the 9th newtons. This was an attractive force between 1 and 3. Remember that we had 1, 2, and 3, which were negative, negative, and positive. So the force on 3 from 1 was attractive, and it went that way. So we could put a negative number in there, but really what we're interested in is the fact that it is to the left. There was also an attractive force on 2. That's the force between 2 and 3, which we just calculated in the previous question. And we came up with that attractive force being negative 4.4 times 10 to the 9 newtons. And in that case, it was also on 3 towards 2, so it was to the left. So we can add both of these together, and when we do that, we end up with 11.5 times 10 to the 9th newtons, and in proper scientific formation, of course, scientific notation, that would be 1.15 times 10 to the 10 newtons, and both of these are acting in the left direction. And there you have it.